Welcome to the High Voltage AI Podcast. In the world of electric utilities, every inch of space, every single design choice, it really shapes our infrastructure. And for the past few days, we've been on a deep dive into the fascinating world of overhead and underground construction. We're exploring the why and how behind each type. This is all part of a special week-long series featured in the PXRD newsletter on Substack, and it's dedicated to equipping electric utility engineers like you with crucial knowledge. Yesterday, we tackled the robust world of heavy-angle framing.
That's right. And today we're shifting our focus. We're looking at a configuration that's become, increasingly vital, especially in our rapidly organizing landscapes. That's vertical framing. We're going to take a deep dive into its unique advantages, its different forms, and the critical engineering principles that govern its use. Our mission for you today really is to give you a shortcut to mastering space-efficient power line design.
That sounds like a really compelling mission. So let's unpack this a bit. When we talk about vertical framing, what exactly is it fundamentally? And why has it become such an indispensable tool for engineers, particularly right now?
Well, at its core, vertical framing refers to power line configurations where the conductors are arranged one above the other vertically on the pole structure. It's a direct contrast to the more traditional horizontal layouts you often see. What's truly fascinating here, and why it's so vital today, are its distinct advantages in a modern context. We're talking about significantly reduced right-of-way requirements.
Which is huge. Right?
Oh, absolutely huge, especially in congested areas. It also offers, improved aesthetic appeal, which matters more and more in urban environments. And beyond just space, it has specific electrical performance characteristics that make it, uniquely ideal for certain applications.
Okay, so it's not just one single solution. It sounds more like an entire family of designs, each kind of tailored for different scenarios. Let's delve into these specific types then. What's the maybe foundational piece in that toolkit, the most straightforward application? And how does it leverage those space-saving advantages we just talked about?
Yeah, that would definitely be vertical tangent framing. This configuration typically features 3 conductors mounted vertically, usually with equal spacing. You achieve this using post insulators or maybe suspension insulators on standoff brackets attached right to the pole.
And its primary use, I'm guessing, for those long straight runs.
Precisely. It's primarily used for straight line runs where the conductor path has really minimal angular deviation. We're usually talking less than, say, 2 or 3 degrees. This makes it absolutely perfect for areas where that right-of-way width is severely constrained, like a narrow urban corridor, or, for those aesthetic-sensitive urban environments where you want to minimize the visual clutter, and the equal spacing provides consistent electrical performance. Plus, its compact vertical profile drastically reduces the overall structure width compared to any horizontal configurations. You're essentially stacking your power lines using that vertical space much more efficiently.
Okay, so vertical tangent framing, clearly efficient for those long, straight stretches where right-of-way is tight. Makes total sense. But the moment that line needs to stop, or maybe we're transitioning from overhead to underground, the forces involved must be immense. How do we apply this vertical philosophy to handle those huge termination loads? That brings us to vertical dead-end framing. And I understand there are a couple of variations here, depending on the load.
Indeed, yes. Vertical dead-end framing has 2 main variations, and each is really designed for specific loading and reliability needs. The first one is the 2-down guy configuration. This setup uses 2 down guys positioned symmetrically, and they support the conductor tensions. Then you have dead-end or suspension insulators handling the electrical isolation.
Okay, and where would an engineer typically deploy this specific type? What kind of loads are we talking about? Moderate? Heavy?
Yeah, it's ideal for circuit terminations with moderate to heavy loading. Think of it for, say, overhead to underground transitions in a busy suburban setting, or maybe as intermediate dead ends where structure reliability is critical, but perhaps not absolutely catastrophic if there's a failure. The dual down guy system does a great job distributing mechanical loads while still maintaining that compact vertical profile. It offers excellent stability even under pretty challenging weather. It's a robust, common choice.
So the 2-down guy configuration sounds solid, reliable for many situations. But you mentioned for those critical circuits where the consequences of failure are just unacceptable, you hinted at something even more robust. What's the option for maximum integrity there?
Right. For situations demanding the absolute highest level of support and reliability, you'd be looking at the 3-down guy configuration. This features 3 individual down guys. Each conductor is supported independently. You'll find this used for really high-loading circuit terminations, or in areas with extreme weather conditions requiring maximum structural integrity, think heavy ice zones or high wind areas. And definitely for truly critical circuit endpoints where any failure would have severe, widespread consequences.
That independent support and redundancy, that sounds like a massive engineering advantage. It's not just more support.
Right.
It's fundamentally about distributing those loads differently and building in genuine redundancy for the critical circuits. Have you actually seen scenarios where a three-down guy system specifically prevented a catastrophic failure that maybe a two-down guy setup might not have handled?
Oh, absolutely. In regions prone to, say, significant ice storms, or even in tornado alleys, a single point of failure in a two-down guy system, perhaps from an unexpected pole shear or a guy anchor failure, could potentially bring down the entire circuit. With three independent guys, though, even if one experiences an issue, the other two often provide enough redundancy to prevent total collapse. It buys crews valuable time to repair without a huge widespread outage. That's the real insight here. It's about grid hardening, but in a compact footprint.
Wow, that's a powerful example. It really shows how these design choices translate directly into grid resilience. Okay, next up we have something called vertical slack span framing. Now that sounds a bit unique, maybe more adaptive.
It is quite unique. This configuration actually incorporates both slack and static tension sections within the very same structure. It creates a sort of hybrid approach that really maximizes flexibility. So with this, the slack tension conductors use their natural catenary curve, that classic sag you see in power lines. Meanwhile, the static tension conductors maintain consistent tension through mechanical systems like dead ends. Down guys support the static tension side, allowing that natural sag on the slack side.
So it's a mix, allowing natural sag on one side while rigidly maintaining tension on the other. Where would an engineer find this kind of hybrid solution most useful? What kind of application?
You'll find this incredibly useful for complex corner transitions where you have significant directional changes occurring, or in areas where adjacent pole placement is severely constrained by, say, challenging terrain or large obstacles you just can't move. It's also ideal for locations where the conductor routing has to accommodate things like roads, driveways, or other existing infrastructure that demand really careful clearance management. The combination lets engineers optimize both mechanical loading and electrical clearances, all while maintaining that vertical profile space efficiency.
That flexibility sounds invaluable, especially when you're battling, uneven terrain or unexpected obstacles in an existing right-of-way. It essentially gives you a custom-fit solution where maybe a more rigid design would require costly reroutes or significant clearing, right?
Exactly. That's a great way to put it. It's about engineering a solution around existing challenges, minimizing disruption and cost, instead of having to clear an entirely new, potentially wider path. It's a truly adaptable design.
Okay, so what does all this mean for those tricky angular deviations? The ones that fall somewhere between simple tangents and full dead ends. Yesterday we discussed heavy angle framing, which handles extreme directional changes. But in practice, you often have these, frustratingly subtle shifts in terrain or property lines. They aren't quite dead ends, but definitely more than a straight run. What kind of engineering solutions bridge that gap within vertical framing?
Yes, that's precisely where light angle framing comes to play. Its design philosophy is specifically engineered for those angular deviations that fall below traditional dead-end thresholds, but still exceed what tangent framing can handle. Its configuration typically uses a bisecting down guy arrangement. This splits the angular forces effectively. You'll use post insulators on standoff brackets or maybe suspension insulators, depending on the loading requirements. And static tension is maintained on the departure side.
Gotcha. And what's the typical range for these light angles? Are we talking 5 degrees, 10?
Generally, it's great for line angles, typically ranging from about 5 to 30 degrees. Though, of course, this can vary based on conductor size, tension, local standards. Think about rural to suburban transitions needing gradual directional changes. Or navigating around environmental constraints like a protected wetland, or maybe property constraints like an existing building. The key advantage here is that this type eliminates the need for full dead-end construction at these moderate angles. That can significantly reduce both material costs and construction complexity while still maintaining adequate structural integrity. It's often a very smart compromise.
Makes sense. And what about let's say, the most robust option within vertical framing itself? We touched on heavy angles in general yesterday, but how does vertical heavy angle framing fit into this specific vertical context? What distinguishes it from maybe the more general heavy angle discussion we had?
Right. Vertical heavy angle framing is exactly that. It's the most robust vertical framing option, specifically adapted to the vertical configuration. It features independent conductor support, using dead-end or suspension insulators on each side of the angle. It's really designed to handle the most significant changes in direction while staying vertical.
Okay, and how does that independent support manifest structurally? What does that look like on the pole?
Well, each conductor side is supported independently. You'll see heavy-duty dead-end or suspension insulators and associated hardware. Plus, you'll typically have multiple downguy systems providing maximum structural stability. This is your go-to for line angles exceeding those light angle thresholds, so typically greater than 30-45 degrees. Also for high-tension circuits requiring maximum structural reliability, and for critical junction points in transmission and sub-transmission systems, maybe where multiple lines converge or diverge. Now, while it certainly requires the most material and labor investment, it provides unmatched reliability for these high-angle applications. It can accommodate the full range of conductor tensions and environmental loading conditions. It's really the powerhouse of vertical framing options.
Okay, switching gears slightly. Beyond the phase conductors themselves, the placement of the neutral conductor is also critical in any power line design. How does neutral positioning differ in vertical framing specifically? And what are the key implications of each approach for an engineer making that choice?
That's a great point. The placement of neutral conductors needs careful thought, considering both electrical and mechanical factors, especially in a vertical setup. One option is the shielded configuration. Here, the neutral conductor is positioned above the phase conductors. This isn't just arbitrary placement, it's done intentionally to provide lightning protection. It essentially acts as a lightning shield for the phases below, and it helps maintain proper electrical relationships between the conductors.
So if lightning protection is absolutely paramount, this shielded configuration is the way to go. Where else would we typically see this shielded approach being used?
Yeah, this configuration is often used in areas known for high lightning activity. Also, for transmission and sub-transmission circuits needing maximum reliability, where any disruption is very costly or impactful, and potentially in locations where induced voltages must be minimized, perhaps near sensitive electronic equipment or parallel communication lines. It adds that extra layer of protection and electrical stability.
Makes sense. And what's the alternative then? The unshielded approach. Why would an engineer choose that instead?
Right, the contrast is the unshielded configuration. Here, the neutral conductor is positioned below the phase conductors. The main advantage here is that it significantly simplifies construction while still maintaining the necessary system grounding requirements. You'll often find this in distribution circuits where maybe lightning protection is considered less critical, or perhaps in areas with more favorable lightning exposure characteristics, meaning statistically fewer direct strikes are expected. It's also a common choice for, let's say, budget-conscious projects where simplified construction is prioritized. It really boils down to a trade-off. Balancing maximum protection against construction cost and simplicity, all based on the specific needs of that circuit and its environment.
This definitely raises an important question then. When an engineer is actually designing with vertical framing, what are the core considerations they absolutely need to keep front of mind? Electrically, mechanically, economically. It seems like every choice has a ripple effect, doesn't it?
Absolutely, it really does. Vertical framing impacts several parameters that require careful evaluation, and they are quite distinct from traditional horizontal designs. Electrically, for instance, engineers need to consider inductive reactance. The vertical spacing creates different inductive characteristics compared to horizontal arrangements. This requires careful analysis during system studies. You can't just plug in standard horizontal line parameters. You really need to reevaluate things like voltage drop and power transfer capability for that specific vertically configured line.
That's a subtle but really critical shift in the electrical modeling required.
Yeah.
What about capacitive effects? Is that different too?
Yes, it is. Then there's capacitive coupling. You generally have reduced phase-to-phase capacitance in a vertical stack compared to a flat horizontal one. This can affect system charging current and potentially voltage regulation, so that needs to be factored in. And perhaps surprisingly to some, lightning performance. The compact vertical profile can actually improve lightning performance in some ways by reducing the overall target area for direct strikes. Though, of course, proper shielding design, like we just discussed, remains critical for actual protection from strikes that do occur. It's a bit counterintuitive, but potentially a real benefit.
That's a good point about the lightning performance potentially improving. Interesting. What about the physical stresses, the mechanics of it all? How does vertical framing behave differently under mechanical loads like wind?
Right. Mechanically, engineers must think about wind loading. Vertical framing typically experiences different wind loading patterns. While the reduced width might decrease the overall wind area compared to a wide horizontal structure, the vertical profile itself may experience different turbulence effects. These need to be modeled correctly. Conductor galloping is another big one, especially in icy conditions. The vertical arrangement can affect how conductors might gallop or oscillate violently. So engineers really should evaluate the local climate history and consider mitigation techniques, maybe things like interface spacers or dampers. And crucial for any design, but perhaps especially for vertical setups, is maintenance access. Vertical framing can sometimes complicate certain maintenance activities, particularly hotline work where crews work on energized lines. So the design absolutely must incorporate appropriate clearances and access points right from the beginning. You don't want to design something that's impossible or unsafe to maintain down the road.
That's such an important practical consideration, often overlooked during the initial design phase. Of course, the bottom line always comes up: economics. How does vertical framing truly impact project costs, not just upfront, but across its entire life cycle?
Exactly. From an economic standpoint, the primary and often most significant advantage is the reduced right-of-way costs. RW. In urban and suburban areas where land can be prohibitively expensive, this factor alone can represent massive upfront savings. It can potentially make a project feasible where a traditional horizontal design simply wouldn't fit or would be too costly from a land perspective. Regarding construction costs, well, while some configurations might need additional hardware like those standoff brackets we mentioned, the reduced structure width can often offset these costs through simplified foundation requirements and less clearing needed. You're building a narrower footprint, which usually means less excavation and site prep. But critically, don't forget long-term maintenance. You absolutely need to consider the long-term implications. That includes access requirements, potentially needing specialized equipment or techniques. Sometimes reduced upfront costs might be offset by higher specialized maintenance costs later on. It has to be a full life cycle cost analysis.
Okay, so putting it all together, with all these different types, these options, and all these considerations, how does an engineer systematically choose the right vertical framing configuration for their specific project? What's the practical application of all this knowledge when they're, sitting down at the drawing board facing a real-world problem?
Right. Choosing the appropriate vertical framing configuration really requires a systematic evaluation of multiple factors. It's a process. First and foremost, you usually start with the line angle analysis. This is often your primary driver. So roughly, for angles between 0–2 degrees, vertical tangent framing is typically optimal. It's the most straightforward and cost-effective. If you're looking at maybe 2 to 5 degrees, you might consider tangent framing but with enhanced guying, or potentially step up to light angle framing. You're just starting to feel those angular forces build up. For the 5–30 degree range, that's generally where light angle framing is the sweet spot, specifically designed to bridge that gap efficiently. And then anything typically 30 degrees or more requires the heavy hitters. Heavy angle or full dead-end framing is needed for those robust solutions.
Okay, so the line angle acts almost like a decision tree, pointing you in the right direction initially.
Yeah.
What else factors in significantly beyond just the angle itself?
Yeah. Beyond the angle, loading considerations are absolutely paramount. This includes the conductor size and type, obviously, as larger, heavier conductors naturally require enhanced support systems to manage their weight and tension safely. Tension requirements are also critical. High-tension applications will heavily favor dead-end configurations because of their inherent strength and ability to hold that tension. And of course, environmental loading, things like ice and wind loading, significantly affect configuration selection. You absolutely must design for the worst-case scenario reasonably expected in your specific geographic region.
Okay, so the environment and the electrical load itself. Got it. What's the final piece of that puzzle then?
Well, finally, you absolutely must weigh the reliability requirements for that specific circuit. Critical circuits, those powering hospitals, major data centers, dense urban areas, they will strongly favor configurations with redundant support systems built in, like those 3-down guide dead ends we talked about earlier. The context of rural versus urban applications matters too. Urban settings might justify additional investment in reliability and perhaps even aesthetics more than a remote rural line. And crucially, as we touched on, maintenance accessibility should always be considered during the design selection phase. Think about the long-term operational ease and safety for the crews. You need to ensure they can safely and efficiently work on these lines once they're installed.
What really strikes me about listening to all these options and considerations is just how much thought goes into balancing these very practical constraints: space, cost, maintenance, with fundamental engineering principles. Vertical framing truly represents a powerful and often indispensable tool in the utility engineer's toolkit today. It offers robust solutions for these increasingly space-constrained environments, while still maintaining crucial electrical and mechanical performance standards.
You're absolutely right. The key, really, to effective vertical framing design lies in understanding that each configuration serves specific applications and, importantly, comes with its own set of trade-offs. There's no single best type for everything. Proper selection, driven by that holistic view of angle, loading, reliability, and economics, can deliver both immediate construction benefits like a lower ROW cost and profound long-term operational advantages. As our utility systems face ever-increasing space constraints, mastery of these principles becomes increasingly valuable for every practicing engineer out there. It's not just about building lines anymore, it's about building the right lines, efficiently and resiliently.
So what does this all mean for you, the listener, thinking about your own projects? How might understanding these nuances of vertical framing empower you to innovate, or maybe solve a specific spatial challenge you're facing in your next design? Think about the trade-offs and the opportunities it presents. Perhaps there's a congested urban corridor you've been struggling with, or a tricky terrain crossing where traditional horizontal methods just won't cut it, or are proving too expensive. Vertical framing might just be the elegant, efficient solution you've been looking for. If you'd like to leave feedback on today's deep dive, or perhaps you have any questions, please feel free to reach out to us. You can email me at alex.reed.power.podcast@gmail.com.
And you can reach me at emma.quinn.power.podcast@gmail.com. We'd love to hear from you.